All right, we're going to talk about average rate of change and instantaneous rate of change. We're going to start off with a polynomial function. I've got negative 0.1x cubed plus 0.2x squared plus 1.5x minus 1. If you're wondering why I use decimals, it's just to keep the graph nice and short. You can multiply all these numbers by 10, all the coefficients by 10, and it'll give you the same concept anyways. All right, so first thing I want to find let's say the average rate of change between x is 5 and x is 6. Right, so what we're saying is, on average, how far did we go up or down for every 1 that we went to the right? Well, this is lucky. I'm actually going 1 to the right, so we could actually just see how far up and down we went. And if we were to continue at that exact same rate of change the whole way through, well, you would have a straight line that basically goes through there. And actually, I have a straight line here to show you. There you go. So if you had a straight line, this blue line is what it would be like if it kept the same average rate of change all the way through, or the same instantaneous rate of change in this case as well. But that's not what happens. This green line actually changes as it goes along. All right? But to find the average rate of change, as we know from before, you just do delta y over delta x. Okay, so our 2 points here are f of 5 comma f of 5, so that's 5 comma negative 1. You plug in a 5, you get negative 1. And if you plug in a 6, you get negative 6.4. And you simply do delta y over delta x. So f of 6 minus f of 5 divided by 6 minus 5. And you have yourself your slope. And the answer is negative 5.4 right here. Okay, so the slope there is negative 5.4. Well, of course, look at you go down 5.4 in that time, and you're going 1 to the right. So for every 1, you're going down 5.4. What about the instantaneous rate of change? Now, in this course, we don't actually teach you how to find the instantaneous rate of change. The instantaneous rate of change would be exactly the slope right at x equals 5. The problem with that is if you plug in 5, f of 5 minus f of 5 divided by 5 minus 5, you're dividing by 0. Right? And so we will give you the tools to actually find that slope right at that spot when you get to calculus. And actually soon, right in the beginning of calculus, you learn that. But for now, we have a number that's just so close. You could take a really good guess at what it is just by using two numbers that are really, really, really close. Okay, so in this instance, we'll just use 5.000001 as our x value, and then f of 5.000001 will be the y value. Right? On the graph, it shows 5, negative 1, but if you look over here, f of 5.000001 is actually negative 1.000004. Right? So it's very close to negative 1. All right, well, when you plug it in and you do your delta y over delta x, you actually get a slope of negative 4.0000130174. Now, is that the instantaneous rate of change right at 5? No, it is not. As you can see, the instantaneous rate of change, like the rate of change, changes throughout this curve. This curve isn't staying the same slope all the way through. So this red one is the one we just calculated, which is very close to the instantaneous rate of change. The blue one is the average rate of change from 5 to 6. So as you can see, this slope is actually getting more and more negative, like greater and greater in the negative direction. It's getting like a steeper and steeper. Right? So we know that because we didn't just do this at 5, we did at 5 and 5.000001, that it's going to be a little bit steeper than what our actual answer should be, right? And if you look at here, negative 4.000013, you have I think you could guess just as well as I can what the slope right at 5 is equal to. And it turns out that yes, the slope is exactly equal to negative 4. So if you're ever taking a test or doing some assignment or something like that, and we ask you to estimate the instantaneous rate of change, it's fantastic that you get an answer of negative 4.0000130174. Great, you could do the math. But if you have a true understanding of this, you're going to have enough common sense to say, therefore, the slope of the curve at f of 5, or at 5 comma f of 5, is probably negative 4. Now you can't say is equal to negative 4 for sure, but we're just estimating. I don't think I would estimate negative 4.0000001300174 because I know darn well that that is not the case. We did not do it right at 5. We did it at 5 and a little bit past. So I know for sure that's, well, almost certainly that that's not it, actually it. But if I take a look at that, I have a pretty good idea of what it is, and it's negative 4. Okay, so when you do your work, please don't give me a conclusion that the instantaneous rate of change is equal to this long number. Just say the instantaneous rate of change is probably equal to negative 4. All right, let's go to another. So that's a polynomial function. We've actually already worked with those, but I thought I'd start you off with that. So let's just take this out of here, and we will name our next function f of x. There we go. All right, now we have a rational function. Again, we've worked with these rational functions many times before. And so you can see that we're going to have an asymptote at 6.1. We're going to have an asymptote at negative 4. And we have a 0, right, at negative 2.333. So at negative 7/3. All right, let's give me some time here. Okay, so what is the average rate of change from x equals 5 to x equals 6? Okay, well, x equals 5, so f of 5 is negative 0.2469135800247. F of 6 is negative 2.5. Right? If you do the delta y over delta x, you're going to get, if I can find it, there it is, negative 2.25308641975. Therefore, the average rate of change from x is 5 to x is 6 is about negative 2.25. Right? So where's that? Right here. Right? If I were to draw a line, the slope of this line that goes through those things would have that slope right there. So would be negative 2.25308641975. Okay, so if I were to write the equation of this line here, this blue line, it'd be y equals negative 2.253 blah 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 x plus 11.019. All right, what about the instantaneous rate of change right at 5? Okay, so we're going to go to f of 5, which is negative 0.2469 blah blah blah, and we're going to go to f of 5.000001 at negative 0.2469. So it's two numbers that are very, very, very close to each other here, right? And we're going to do delta y over delta x right here, and we get an answer of negative 0.203267. So you see the slope again is less than the slope from 5 to 6. Okay, and so it's just touching right at 5 comma negative 0.247. So if someone was going as fast as what, like going up and down at this rate, and they just kept staying at that rate, well then they would just go along this line, they wouldn't move. But this curve doesn't do that. This curve changes the rate as it goes along. Right? So, and by the way, we know this is just an estimate of the instantaneous rate of change. So please don't say therefore the instantaneous rate of change is. You can only estimate it at this point. Okay, so what is that estimated rate of change again? And it is about negative 0.203267, let's say. All right, so as you can see, basically the lesson here is saying all you have to do is be able to plug in x values, and you're going to do the same thing over and over and over and over. All right, so let's try a log. All right, let's call this one f of x now. Bring it up to the top. Get rid of this one. All right, so now logarithmic function. What do you have to do? All right, find the value of f of 5. find the value of f of 6, plug it into this formula right here, and we have ourselves our slope, 0.074525. That is the average rate of change between 5 and 6. All right, let's check out. There, the slope of this blue line is also the average rate of change between 5 and 6. What is the instantaneous rate of change at 5? Well, we're going to estimate it, and that is going to be right here, 0.07973 approximately. Right, so as you can see, these two graphs are actually very close to each other. Right, so almost the same thing. So on this log curve, we see that the slope doesn't change very much. It does change. You can see that the two numbers, this is 0.0745252. Here we have 0.0797. So this one is actually a little bit steeper. So that means, something we already knew, this log curve is getting less and less steep as it goes to the right. And you can see off to the right, see how the green is getting less and less steep than what the red is. The red is the tangent line right at 5. If the log function were a straight line, it would follow that, but it's not. It's getting less and less, and that's why from 5 to 6 your slope is a little bit lower. All right, we're done with that one. Let's go to the next, and we've got, here's a sinusoidal function. Let's call this one f of x. F of x. Not doing too well here. F of x. There we go. All right, bring it to the top. And same thing. We're going to plug in a 5 and a 6. Right? F of 5 is 6.89 approximately. F of 6 is 7.804 approximately. And delta y over delta x will give you the slope of this blue line right here. Right? And it's also the average rate of change of this sine curve from 5 to 6. Right? Let's check the instantaneous rate of change, or at least an estimate of it. And there we go, right about that point. The instantaneous rate of change is, that's right here, is about 1.2607. Remember, the average rate of change was about 0.91. So it's a bit steeper at 5 than what it is between 5 and 6. Well, yeah, we can see that. It's on its way down. Right, let's go. So here's the steepness of the curve. The blue one is the steepness of the curve that goes, or of the line that goes through 5 and 6, and the red one is the steepness of the line that just touches. It's just tangent at 5. And last but not least, let's do a combination of a bunch of functions. So you got a log in there, you got a rational in there. We've just combined a bunch of different things, and it's a nice weird curve here. All right. Again, super easy. Find f of 5. So plug in 5 and you get negative 24.661 approximately. Plug in a 6. 6 comma negative 16.526. And then you put it into delta y over delta x, which is right here, and you get a slope of 8.13 approximately. So from here, the average rate of change, you're actually getting much higher over, well, this is incredibly different from the instantaneous rate of change. The instantaneous rate of change is almost straight up and down, right? So you're going super far down, whereas the average rate of change actually goes upward. Well, what happens there? Well, you actually have an asymptote in between there, and it kind of comes back on the other side. But on average, if you start off, if I'm at negative 24.661, and then 1 minute later I'm at negative 16.526, doesn't matter how I got there, on average, my speed was between that and that was about 8.1347 per minute. Well, yeah, we went up by 8.1347 in 1 minute. So that's exactly what the average is. And the instantaneous rate of change, if I were to actually continue along this path, right, the actual slope that I'm at right at 5, well, I would go down in that 1 minute. I would go down 110.47 approximately. Right, so if I go all the way down to 110.47 minus 24 points, so it should be about 135 is where it's going to cross that line. At positive 6, sorry. It crosses 6 right there. There. At negative 135.129. To summarize, if you have any function that exists that has at least 2 different points, then you can find the average rate of change between those 2 points, or the 2 x values of those 2 points, simply by plugging in those 2 x values, finding the y values, subtracting them, and then take the 2 x values, subtract them. Make sure you keep them in the same order. If you do f of x2 minus f of x1, then make sure you do x2 minus x1. And that will be the average rate of change, also known as the slope between those 2 points. It's also the average slope of those 2 points, you can say. So the AROC is also the average slope between those 2 values. And it's also the slope of the secant line that you can draw that crosses the curve at those 2 x values. Right? So the instantaneous rate of change, now we only know how to estimate it for now. Now it doesn't matter how complicated the function is. If you have a function that exists from x1 to x1 plus h, in other words, it just has to exist in this little teeny area around x1. And h, let's just call it very, very super small. So think of h as 0.000000001. The smaller you get h, the better your estimate. So especially with a small h, then you can estimate the instantaneous rate of change, otherwise known as the IROC, right at the point x, or x1 that we've chosen, and that would be, the slope is going to be f of x1 plus h minus f of x1 over x1 plus h minus x1. Well, x1 plus h is your second point. There's just a teeny bit to the right of x1. So you got x1 was where we want to actually estimate the instantaneous rate of change. x1 plus h is just this little bit to the right. And when you take the point that's a little bit to the right and you subtract x1 itself, you're always just going to be left with h, right? So it's like 5.0000001 minus 5 is just going to be 0.00001, right? And on the top, it's the y value, the difference in the y value over that small amount of time. And this is going to be an estimate of the instantaneous rate of change. So like I said, it's not going to be exactly the instantaneous rate of change unless you happen to have a straight line at that point, or at that area, in that area, which is rare. But it is a very good estimate if you get h to be as small as you possibly can. All right, so IROC is also the instantaneous slope at that x value, and it's also the slope of the tangent line that touches the curve at that x value.